So today it will be chapter 3. Just to recap what you now should know from chapter 2. You should know about sources, and there we are talking about real sources. Then we have ideal sources, and from ideal sources we had two types: effort source and flow sources. You should know about loads, which we now call resistance, linear, nonlinear, whatever, and what equation you will get when you have a coupling here between effort and flow. That we will have effort equals resistance multiplied with the flow. You should know about transformers, and you should know about gyratos. So that is roughly what you find in chapter 2. So topic today, chapter 3. It's just called simple dynamic models, and it's sort of say the essential part that we need to start formulating or solving real problems. So I'll just pick the essential parts here that we need from chapter 3. Simple dynamic models. And the first ones that we are going to need to know about, something called a compliance. Compliance. And there we use a letter C to describe him. Compliance, something that will give after when you try to force him, when you push on him. In Norwegian, føyelighet, a little soft. Somebody is giving you a hug, you sort of get smaller if it's a very strong guy that hugs you. Compliance, something soft. Physically, to make it simple, think in terms of a spring. That is maybe the simplest description of it. Linear spring. So compliance, say example, spring. So you have a force attacking a point, and this point is then connected to a spring, which then is connected to a solid wall. Now if you push this spring together, you squeeze him together, but the further you go, the more force you have to use. And the connection there, typically a distance x, sort of how much you have squeezed this spring together. Then you will have the following connection: force equals x, and then a spring stiffness, k. Okay. Spring stiffness. This is a linear explanation, a linear equation for a spring. They don't have to be, it doesn't have to be constant. It could be a messy expression, but unless someone tells us otherwise, we will treat him as a linear spring. With a compliance, we use the reciproc. So the spring stiffness, that's actually now 1 over the compliance. So obviously here, if you use a force and do the work here, you squeeze this spring together and then lock it. Then this squeezed spring will contain energy that can be used at a later time. So we are talking about energy storage. Yes, this C element is an energy storage element. C is an energy storage element. Like with the resistance, you can't store energy in a resistance. He will eat the energy. He will use it, producing a little bit of heat, and then the energy is lost forever. But a spring, no, that is something where we contain energy to be used at a later time. When we now think in terms of a generalized compliance element, generalized C element, we will have the following, like that. So this C element, compliance, is also a one-port element. So one arrow hitting into it and nothing more. As in comparison to these transformers, they were two-port element, transformers and gyrators. So something went in and then something went out on the other side. Not with the C element, only one port. So here we will have an effort, and here we will have the flow, F or Q dot if you like. Now, what is the connection between them? Well, in general, you will then see here the force is given by here, not the flow, but actually the time integral of the flow, and then divided by C. So here, if we go this way around, here, and then go back to the effort, what will the effort be if you knew the flow? Well, the effort would now be equal to this Q, but without the dot. So here is the explanation why we have used this Q dot all the time and not the F. So we are taking actually the time integral of this flow, and we will have just Q divided by C. And this is sort of the definition, you might say, of the C element, or a spring element, or compliance element. Sometimes we will have to go the other way around. So we don't like it, but sometimes we have to. Meaning, you don't know the flow, but you know the effort. So we go the other way around. So you have the effort here, and the effort hits this C element and come back and returns on the other side. Now the flow. We should have a Q dot. How can we get a Q dot? Well, you go back to the definition here, multiply with C on both sides, and you see then you have a Q. But I don't want a Q here, I want a Q dot. Okay, then I take the time derivative of effort multiplied with C. Now if this c is just a number, then of course he goes outside the time derivative. If he's changing with time, okay, then you have to take the time derivative of him as well. The effort, and then typically he will be a variable, so he can change with respect to time. So in short, this is how we like it. This is something we do not like, but we can do it if we have to. Okay? Other spring elements. Should be a long list here somewhere. There's too many words in this book. Boring. No, it's dropped out. Never mind. We can easily draw them. So this is mechanical translatoric C element, a linear spring, or maybe nonlinear. If it's nonlinear, that means this C is not a constant. It can be a function of whatever, but we still use the same definition. If you have the mechanical rotational C element, well, that's like you are winding up an old clock. So then you will have something like this. You add a torque. So he will go round and round, and then you wind up a spring. Sort of the same symbol as with the translatoric mechanical. But now it just goes round and round and round. Of course, there will be limitations with the spring, both here and also in the mechanical world. You can't squeeze him down to more than 0. So there's something we have to be careful with when it comes to programming. You have some other mechanical springs as well. If you take a solid rod out of a wall, sort of a stiff beam, but it's a little bit elastic. Could be rubber, could be steel, wood, if you don't force it too much, and then you can sort of rotate him a little bit. Or you could have pushed him up and down, sort of vibrate a little bit. That is also act like a spring. What about in the fluid world? Say you have a big reservoir, big lake. So here you have a sea depth h. Then here at the inlet of a pipeline, you will have a pressure which will be rho g h. And here, well, if the liquid starts to flow, then you might get a pressure drop due to the velocity, like minus 1/2 rho v square or something like that. But say this is small. So we treat this reservoir now as a pressure source, an effort source. So the pressure here is given. Down here I now insert a storage tank like this, and then I continue. Maybe here I have a vent of some kind, and then it flows out. This storage tank will now act as a fluid spring. So here we will use a C element to describe this storage tank that can have dynamical behavior, depending on the problem, of course. So what will this C element be? Well, for a fluid, we here are going to need the surface area A. And if I recall correctly, this C will now be defined as surface area divided by rho G, like that. How will that help us? Well, what's the effort in fluid? So, fluid mechanics. Then we use the pressure as the effort. What about the flow? That should now be the volume flow Q. Okay. What was the connection here? Well, the pressure should be equal Q, the small q, that's without the dot. Now what's that? Well, here for the volume flow, that's Q equals cross-sectional area multiplied with a velocity. What is the time integral of Q dt? Well, cross-sectional area is the same, of course, but the velocity now becomes just a distance. So what are we talking? The time integral of him will be just a volume. Okay, so according to the definition here, this one should be now the volume, which then should be cross-sectional area multiplied with the distance. And then, of course, we are talking about this distance to find the volume in this storage tank. Then divided by C. Okay, we have A multiplied with X divided by C. C we have here. Divide by C, that will be A under here times rho G. The area falls, and you see the pressure is given by rho G X. So actually you'll find the pressure here, or actually here. Pressure rho G times the depth X. So that is a storage tank acting as a spring in fluid mechanics. For an electric system, you will have two plates close to each other. So that's just what we call a capacitor. So in Norwegian, that's a kondensator for you. So electric. So the symbol there would now be just two parallel plates, and then maybe here you go to ground. So that is a C element for a capacitor. So that is actually all we need to know for a C element. And the important part, effort equals Q divided by C. That's sort of the definition for any compliance element, any C element. We will use C elements for a lot of different things where one might not think it's not a spring really. But it will be more of that later when we are looking more into different examples. We need some more definitions and tools before we can really start with bigger examples. So I will stop with the C element here and now continue with the next one, which then is called inertances. Inertances then we are talking mass. Let's see here, where are we? Fluid. Yeah. That's another fluid spring. So it doesn't have to be liquid. If you take a chamber and then you squeeze in a gas, a pressurized gas inside that chamber, that will also act as a spring. And then depending on the gas and what model you use to describe it, ideal gas law or adiabatic or whatever, could be linear, non-linear. So you'll find a little bit about it here. Here, some floating block in the ocean. So when you tilt it a little bit, he will then sort of produce a torque back again. So this will actually also act as a spring. Of course, with the fluid motion here, you will have damping, but still you can model this behavior with a spring instead of looking at forces, buoyancy, stuff like that. Inertances. Here we go. Inertances. Three, two. Inertance, a large I. Inertance in Norwegian, inatans, but if you need to describe it more straight to the point, call it a mass. Very simple. That's actually what it is, a mass. And the inertance has also energy storage capacity. So, example from mechanics. So here you'll have a lump, and he may be moving or may not be moving. Anyway, this M is just equal the inertance I directly when you are talking about translatoric motion back and forth. So of course, if you have a mass given some velocity, this mass contains energy, mechanical energy that we can use to something else at a later time. So yes, I is also an energy storage element. If you have mechanical rotational, what do we have then? Rotational mass. How do you describe that in mechanics? Then we are talking about the moment of inertia. So here, if you have, say, a flywheel that rotates, and this wheel is heavy, starts to spin, then the I here equals 1/2 times the mass times the radius square. Radius here, if you have a steel wheel or a coin or something that rotates. So that's the moment of inertia, treghetsmoment in Norwegian. So where does this formula actually come from? Well, typically in mechanics you will look it up into tables, mechanical textbooks, depending on the geometry of the object that is rotating. But in general, this I, he will then be actually the sum of all small masses multiplied with the distance squared from the point of rotation, or the center of rotation. So you can either sum it up, all the small masses, or if you want to do it mathematically, integral r square dm. So it's just sort of accumulated up depending on how this object actually is looking. Fluid mass. Well, it's not just the density here. We are talking about a little bit more. We have the density, but the density rho, but you need also the length of this fluid string divided by the cross-sectional area. So if you have a pipe here and you have a volume flow, then you have a cross-sectional area A, and then also you need the length of the entire fluid string. So if it's a very long one, of course you have a lot of inertia on it, large inertance. But if the cross-sectional area gets big, then actually the inertia goes down. One might think the opposite here, that big cross-sectional area should produce a big mass. Well, that's true. It's more mass inside, but not when it comes to the inertia. We'll have the explanation for that later. And the final domain, electric. Yes, we have masses in electric domain as well. You have the symbol, it's just a coil, something like that. And we call it an inductor. The definition, let's see. For the generalized inertance, you have a bond hitting the I element. And again, you will have the effort on top, the flow under, and we need a coupling between them. So here you have an effort, and down here you have a flow. And this flow, typically we call this one for Q dot. The effort, we could use a P dot. So that's a little bit actually up to you how you describe this. What letters do you want to use? E or F is fine, or P dot and Q dot is fine. A little dangerous with this small p, of course, because this P is nothing to do with fluid mechanics for the pressure. Very dangerous. Remember here in fluid, what is the effort in fluid? Well, the effort, that's actually the pressure. So here is big room for misunderstandings. This P stands for actually momentum, not pressure, in the generalized version. Okay? So that's normally you will use a small e. But the definition now for inertance, the way we would like to do this, then we know the effort, so we want to go this way into this element and go down, and what do we get? We should get the flow. He will then be given as the P without the dot. So again, we are talking time integral of this effort divided by the E element. So this is the definition of an inertance. This is how we like to use it. So this, very nice indeed. And then sometimes, yes, we have to go the other way around. So we have the flow down here, Q dot, and now sadly we have to go here and find an effort. What will the effort be? Well, the effort should be a P with a dot. I can find a P alone, but then you see I have to take a time derivative. So the effort equals time derivative of, what will it be? Well, it will be the flow that we had, Q dot, multiplied with the inertance. So this is also an option. We don't like it, but we are capable of doing it if necessary. Okay, so that was our two energy storage elements, compliance and inertance. And that's all we have that can store energy, those two. Here you have some examples. Examples of constant inertias. They don't have to be constants. Of course not. This electric one can be tuned in with some maybe even mechanical devices that can change the inertance for it. Rotational, I have a nice example there we will take now. Fluid tube, you can just change the cross section here a little bit for a part of the pipe. Then you change the inertance, at least for that part. But if the cross section is constant, then the inertia will be constant. So here you have sort of the definition for the momentum of inertia. Now, I can keep that one. Now do the following experiment. If you take a cylinder like this, an inner cylinder, and then an outer cylinder, like you wind up, say, a thin wire, like if you want to sew something. So you have a thin thread winded up here on this inner cylinder, and then you drag it out here. Of course, this construction, this cylinder, may be small, tiny. That's if you want to use some thread and needle, some handiwork. Or it can be a very big one, like the guys that put down these very thick cables, electric cables, or maybe a heavy steel chain that is winded up on such a big roll. Now, first question. If I drag in this thread here, what happens? Which way will this cylinder move? This is a trick question. Can anybody imagine which way it will go? Will it start moving to the left or to the right? I assume that he doesn't slide on the table. Which way will he move? So he should be moving to the left. So when you drag here, you sort of unwind the thread and then he should roll backwards, right? That's wrong. You don't believe this until you try it. He will actually start to move against you, towards you, and the bigger this inner radius is, the faster he will move. He will really speed up against you. Just try it with a small thread, a cylinder with a thread on. Very strangely. Why? And why? I mean, the intuitive picture here is you pull here, and then this circular object will start to rotate around the center point. But he doesn't do that. He doesn't rotate around this point. Look at a car that drives by, or a bicycle. You see the wheel go round. At what point does this wheel rotate? Well, if you're sitting on a bike, then you know he's rotating around this point. But when you're standing on the ground next to it, he doesn't rotate around this point. He rotates around this point. This point is fixed, it doesn't move. So when you pull here, you will actually create a rotation around that point. So yes, he comes towards you very, very fast indeed. Just try it. Okay. Now, forget about this small little cylinder with the needle and the thin thread. Think of it as a very huge one, very big cylinder, many tons, and we have a heavy steel chain or something here. And this one now is standing on the ground, and then I kick him. I give him an initial rotation. So of course now he will start to unroll the chain and start moving to the left. Now I don't use a force here, so this will now just drop on the ground. When he moves, he will just unroll the chain. This chain is heavy, very heavy, many kilos per meter. So when he moves, he will lose mass. He will lose rotational mass. That means this inertance, momentum of inertia for this object is not constant. The mass is not constant here. Well, actually the mass is, but not the inertia. So what's going to happen? Well, if I say the cylinder itself typically is made of wood when you see these guys working. So it's not that heavy compared to this very heavy steel chain or whatever it is. So I forget about the mass for the cylinder itself. I just look at the mass for the actual chain here. Very heavy chain, okay? What is the equation of motion for the rotational object? Well, the net torques that attacks any object will produce a change of what we called spin. That was the inertia, the inertance, moment of angular momentum, and then multiplied with the rotational speed. Call it omega if you like, or that's the same as phi dot, angular velocity. But for this problem here, I just kicked him initially. I gave him an initial rotational speed, omega 0, say, initially, and then I just leave him. The gravity is not acting. The gravity goes straight down, so there are no torque acting on him. Hence, the net torque should be 0, meaning the spin has to be constant. Okay, what's going to happen? If the spin is going to be constant, okay, I multiply with omega equals constant, meaning omega equals this constant divided by the inertance. which is becoming smaller and smaller and smaller, the more mass he will drop. So this one, he will start quite slowly, the initial speed I gave him, and then when he loses mass, he will accelerate. Going faster and faster, he will go through the speed of sound, then he will go through the speed of light and go even faster. As long as this mass for the cylinder itself is a 0, and the only mass we have is the steel chain. Just try it. So no, these inertances, they don't have to be constant. They can be a function of different things. Yeah. This one, tetrahedromostate, I would suggest you skip it. If you want to have a look at it, please, but I don't understand it, so if you want to try, please. Nothing that we need. Here, little table describing different examples of elements. Compliances, inertances for the translatoric mechanical world. Ordinary spring, 1 over the spring stiffness. And here a stiff rod or a beam that we can move a little bit. Then the elasticity and things enter into the equations, tricky. Buoyancy effects, okay. Inertance, well, that's just the mass. Rotational world, well, roughly the same as we have seen. Fluid, yes, we have described this already a little bit. And here also a gas pocket, sort of a pressure tank. Also something that we will look into. Some examples there. Okay. Any questions so far? Then we take a break.